Hi, this is lecture number 48 on subsurface drainage design. So, in this mainly we will be working on the unsteady state flow to drains. I mean the previous lecture we were talking about steady state conditions, now unsteady state conditions. So, let us see how the unsteady state conditions, for example, here the falling water table. So, this is observed during the irrigation, when you are applying irrigation or the suddenly it's the water table has fall down. So, Glover-Dumm equation will be used in order to simulate the falling water table in case of the drains. So, Glover-Dumm equation is used, basically the falling water table after sudden rise due to an instantaneous recharge. So, under equilibrium, so we in steady state condition we assume that the system is under equilibrium. So, that the Q which is recharge taking place will be equal to drainage out, but whereas if there is a sudden instantaneous change in the recharge, that definitely influence the drain discharge. So, this is the typical situation in irrigated areas where you apply irrigation and the shallow water table goes down and then after irrigation it again falls down, something like that. So, basically when h less than small d less than L, the flow to the drain is essentially horizontal and it follows that q x, for example, here. So, in this schematic if you see, so this is the drain, I mean tail drain point, this is the halfway of tail drain. Okay. So, there is another tail drain somewhere other place. So, for example, so this is the water table, right, this is the water table, and at the midpoint this is h t, okay, this is the head at the midpoint and this is the drain depth, okay, and d h x by d x is the change in water table with distance. So, from here if you see the x is going this direction and h they vertically upwards. Okay. So, we are going to see how the change in Q is influencing the H. Okay. So, since H is smaller, H is very small compared to the drain spacing. So, mostly the horizontal flow is influencing, and if you assume a unit element in the flow media, right, in the soil media, that has a del x. So, q x which is taking place will be equal to k into d h into dou h x by d x. This is from Darcy's law. So, from Darcy's law q x will be taking place through this will be equal to k into hydraulic conductivity into d h, right. So, d h is the elemental the depth, and then for the unit width, and this is the hydraulic gradient. Okay. So, this is one thing. Then after that, if you use the water balance element, I mean the water balance for element delta x, suppose this is the element. So, you have seen this is the delta x. So, here q x, right, and at this point this is q x plus delta x. Okay. So, and let us say this is a q. Okay. So, the water balance will be equal to, so the change, so the q x, so this is the difference input minus output. Okay. So, here this is all input which is taking place q plus q x plus d x and q x. Okay. This is the output, for example. So, q x plus d x plus q into delta x, right, q into delta x. Delta x is the width, the thickness, sorry, width of the element. So, that is q into delta x is taking place, and q x plus delta x and q x, this is the difference, that will be equal to change in the storage. So, change in storage q x plus delta x minus q x by delta x will be equal to, plus q is equal to delta q x plus delta t into mu. Okay, so this is delta x is divided in both sides. Okay, so limit delta x, when delta x tends to 0, delta a q x by dx plus q, which is equal to delta h x by delta t into mu. Okay, so combining 1 and 2. So, this is 2 and the previous equation, Darcy's equation, if you combine, right. So, q of, so you are substituting for q x. So, q x is equal to k into d h into delta h x by delta x, right. So, you can substitute this here, okay, substitute this here and arrange the terms. So, you get delta h x by dt is equal to k into d h by mu delta square h x by delta x square plus q by mu. So, where this equation is called Bossiness equation. Okay. So, this describes the water table and unsteady recharge. So, now you are going to integrate for no recharge q equal to 0 and the boundary conditions, initial boundary conditions, we are going to find out the solution. So, for example, the 0 for the 0 recharge. So, what will be the solution for this equation? So, that will be the initial conditions are h x 0 is equal to h naught, right. That is the initial water table, and the boundary conditions are when x equal to 0, right, and so when x equal to 0 and any time h is equal to 0 at the drain, okay, drains at the drain. So, suppose here you have this is x and h. Okay. So, when x equal to 0, so h is 0 and suppose you have another drain, right, that is at L length L. So, h is equal to h of L into T. So, here also h is equal to 0. Okay. In both cases drain number 1 and drain number 2, the h will be 0, that is the meaning. So, this yields Glover-Dumm equation. So, according to Glover-Dumm, the mid spacing water table head h t at time t relates to the head h naught. Okay. H naught is the highest water level. Okay. That is h naught, initial water table, you can say initial water table. So, h t by h naught. So, using these initial and boundary conditions and then the equation. So, if you solve it, then it leads to h t by h naught is equal to 1.16 e power minus alpha t, where alpha is equal to pi square k d by mu L square, where pi square can be replaced with 10 k d by mu L square. Okay. So, and the terms are defined here. T is the time, h naught that is in days, h naught is the initial water table, h t is the water table at time t, alpha is the reaction factor which is d power minus 1, and mu is the drainable porosity, L is drain spacing, and d is equivalent depth of impermeable stratum, and k is hydraulic conductivity. Okay. So, this equation will give the water table at any time t, right. So, the next is, so the same thing if you see. So, at time t equal to 0, that is h naught, at time and greater than t t greater than 0, that is h t. Okay. So, d is the small d, and the combining above equations. So, you can find out the drain spacing L between the two drains is equal to 10 k dt by mu into ln of 1.16 into h naught by h t power minus 1. Okay. So, from the previous equation you can find out the drain spacing formula using Glover-Dumm equation for unsteady state conditions. The shape of the following water table, it is a fourth order, because 1.16, I mean if you can rearrange the terms. So, you get the shape in the fourth order parabolic term. In the pipe drain, in case of pipe drain, radial distance are taken into account by replacing the depth d to the impermeable substrate by Hoogout equivalent depth d, okay, makes the Glover-Dumm equation applicable to pipe drainage. So, Glover-Dumm equation I mean this is equivalent to pipe drainage when you use the equal depth concept here, like there is a two conditions. So, if you use this equation along with the two conditions, d is a function of capital D, small d is a function of capital D. So, then the formula can be used for the tail drainage systems. Okay, so here is the exercise. First, find the drain spacing L for when t equal to 0, h naught equal to 0, water table at soil surface. Exactly, the water table is at soil surface. Okay, so here initially, and t equal to 4, h is equal to 0.8. So, when t equal to 4, h that means the h is increased, that means the water table went down, that is 0.8. So, the solution here is h naught is equal to W minus h naught. So, W is 1.2. So, minus 0, that is 1 point exactly at the soil surface. H 4, that is a W minus H 4. So, 1.2 minus 0.8. So, that will be 0.4. Okay. So, from 1.2 to 0.4, the water table has dropped, and knowing the k values and u values and mu values, and with this water table fall, so find out the drain spacing. So, that is the question for this. So, now from the Glover-Dumm equation, so h 4 minus h naught, this is h 4 means t is equal to 4 days and t equal to 0, 0.4 by 1.2 which will be 1.16 into e power minus alpha t. Okay. And so, this is 0.33, 1.16 e power minus alpha t, and e power minus alpha t is equal to, and finally, alpha t will be 1.24, and when t is equal to 4, alpha is equal to 0.31. So, now L square, use the Glover-Dumm equation, L square 10 k d by mu alpha, right. So, 10 2 d, so all values are given, right. So, this is not given, of course. So, k is given, mu is given, alpha we estimated, and finally, L square is equal to 1290 into d. Okay. So, now L, since L is equal to a function of d and d is a function of L, a trial error function procedure is to be followed. So, that is what we explained. So, the Glover-Dumm equation can be applied to tail drainage by considering the equivalent depth concept. So, here the equivalent depth concept, if you bring from Hoogout equation, the small d is a function of capital D. Okay. So, here, so what we do, we initially take L equal to 30 meter, that initial guess, and from this equation knowing the capital D, right, L by 4, now find out L by 4 and see whether which equation is falling under, and then find out small d. Okay. Now, substitute it in this equation and find out capital L. Now, this is 53.3 meter. So, for 30 meter initial guess, you get 53.3 meter. So, this is not a good guess. So, now what we have to do? You have to go for another guess, L is equal to 60. So, always go with the last, I mean the determined value as the initial guess, so that it converges faster. So, then L is equal to 60 meter and D is equal to 2.84 if you follow the same procedure. So, then so the new solution will be 60.5. So, when it is 60, you are getting 60.5. So, L is equal to 60 meter is the right solution, spacing for solution. Okay. So, this way you are going to estimate the spacing using Glover-Dumm equation by recalling the equivalent depth concept. Okay. So, there is a indirect method of solution. So, Hoogout simple equation by eliminating the the flow, the horizontal flow above the drain space. So, then that is L square 8 k d h by q, because we are only considering the flow below the drain space. And then Glover-Dumm equation L square 10 kd by mu alpha. So, combining these two, you get h by q is equal to 10 by 8 mu, right, alpha. Okay. So, this is and the same equation. Okay. So, the same so h by q into 10 by 8 mu alpha. Okay. For mu equal to 0.05 and alpha is equal to 0.31, h by q is equal to 80.65. Okay. So, and so these values are taken from the previous exercise and previous example. Then h by q is equal to 80.65 in Hoogout equation with k equal to 2 meter per day, right. So, L square is equal to 8 k dH by q, okay, and L square is equal to 8 2 into 80 point d and finally 1290 into d. So, you are going to get the, so I mean this is from Hoogout simple equation, and then L square into 8 2. So, find out, I mean put the values here, h by q values, h by q is this, and then other values, and finally L square is equal to 1290 into d. So, this is same as the previous example Glover-Dumm, actual Glover-Dumm equation when we use. So, this is the final, you know, the equation will be like this, and then after that you can find out, make the initial guess of L and find out D, right, and find out the new L. Now, you just check these two L's whether they are equal or not. If they are not equal, again this value as the initial guess and find out D and find out new value and see again whether they are equal or not. So, we will follow the same procedure here. So, this is a simple, I mean this is the indirect way of giving solution when you combine the simple I mean simple Hoogout equation with the Glover-Dumm equation. And then other one is a fluctuating water table, one is falling water table that we have seen using Glover-Dumm equation, the other one is fluctuating water table. So, this is basically using the Dizu and Hellinger formula. So, in this so main thing is a Hoogout simple formula we will be using this one, and then so this may be developed to show the non-steady response to periodic rainfall and irrigation. So, you will be using the Hoogout simple formula in the following, you know, steps to see to determine the fluctuating water table situation. So, in this equation the drain discharge Q is linearly related to mid spacing water table head H t. So, if you see here Q is equal to 8 k dH T by L square. Okay. This is from your Glover-Dumm. So, H t is a H and small t. Okay. So, Q and H t are linearly, so proportionally linear related. Okay. So, now so from this is simple Hoogout equation. So, you just rearrange the terms here and Q is equal to 8 q d small h t by L square. So, now differentiate this dq by dt 8 q d L square dH by dt here, right, dH tt by t basically. Okay. If the groundwater body is recharged by rainfall or irrigation, for example, here. So, this is the recharge or irrigation or I mean thing, and Q is taking place here. So, if R minus Q is greater than 0, so R minus Q, so suppose this is Q is taking place. So, R minus Q is greater than 0. So, that means the water table, I mean water is adding, right, water is adding. So, water table is going to go up. Okay. Whereas, if R minus Q less than Q, so that means the water table is going below. Okay. So, that means the water, I mean the drain is drain is taking place, right, the drainage is taking place through the drains, and crop is taking its water as a crop water uptake. Okay. So, with this concept and with this formula, we are going to develop the fluctuating water table, the equation for finding out the fluctuating water table. So, water table fall is happens when r minus q less than 0, and water table rise happens when r minus q greater than 0. Okay. So, with these two conditions, we are going to develop equation like this. So, the water table fluctuation may be described by dH by dt, which is r minus q by C q. Okay. dH by dt is equal to r minus q by C q, where C is the correction factor and mu is the drainable porosity. Okay. So, during the recession, the water table will not remain horizontal, but fall more rapidly nearer to the drains. Okay. So, now combine 1 and 2 equations by taking point 8 as C. So, dq by dt is equal to 10 kd by mu L square into r minus q. So, this is the equation when you combine the dH by dt, the change in the water table, that will be equal to r minus q, the effective recharge, you can say C by q. So, which is equal to, so this can be written as alpha. If you recollect, alpha is equal to, in the previous slides, k d into mu L square. Okay. So, now you can put this value as alpha and alpha into r minus square. So, finally, what we got is dq by dt is equal to alpha into r minus q. Okay. This is the equation we got. So, the change in drain discharge dq by dt is proportional to r minus q. So, this is true, and integrating the above equation between t, when t equal to t, between t and t minus 1, that is q 2 and q t minus 1. Okay. So, if you can integrate that, so you are going to get integrating dq by r minus q divided by alpha into dt. So, r minus q t by r minus q t minus 1, this is exponential of minus alpha into dt. Okay. So, then q t is equal to q t minus 1 e power minus alpha into dt plus r delta t 1 minus e power minus alpha into dt. Okay. So, this, once you get this, we have to use the simple, this is all arranging the terms basically. So, delta t will be the same, but r minus q into t. So, that will be what, r t minus q t. Okay. Similarly, r minus q, r t minus 1 minus q t minus 1, and if you can rearrange these terms, you are going to get the final equation q t is equal q t minus 1, right, e power minus alpha into delta t plus r delta t into 1 minus e power minus alpha into dt. Okay. So, then since q is equal to 8 k dH by L square, which is equal to 0.8 into alpha into mu h, from this is from indirect solution, if you recollect indirect solution. So, then substitute for, so q is equal to here 0.8 into alpha into mu into h. So, q t means alpha into h t, right. So, substitute q t as 0.8 into alpha into mu h t, right. So, here 0.8 alpha mu h t. So, similarly, here 0.8 alpha into mu h t. Okay. So, then you take common. So, this gets cancels out, and finally, 0.8 mu alpha will be in the denominator. Okay. So, this way, so not only discharge, the recharge. So, h t, the water table height also can be, the water table position at a particular time can also estimated. So, the above two equations may be used to simulate drain discharge and water table depth fluctuations on the basis of weather records given in the value in the reaction factor alpha. So, based on the alpha you can estimate QT as well as HT. So, here is an exercise, an example, water table head and drain outflow calculations on the basis of Dewey-Helling formula. So, here W is given, L is 40 meter, KD is given, mu is given. Okay. So, calculations here, alpha you have to estimate using this formula. So, that will be 0.31 and delta t is let's say time interval like 1 day, and e power minus alpha delta t, that is e power minus 31. So, which will be 0.73, and another term you have to find out 1 minus e power minus alpha delta t, that is 0.27, and finally 0.8 into mu alpha is equal to 0.012. So, we are going to use these values in the equations. So, this is we are going to see those equations in the next slide. Okay. So, and even I would go the next slide. Okay. Here at the start of the rain, the 0th day, the water table head is 0.1, right, 0.1 meter, that is given, the value is given, and the mid spacing water table depth. So, H, capital H is equal to W minus H, 1.2 minus 0.1, that is 1.1 meter below the soil surface. Okay. So, initially the water table head is 0.1, okay, and that is at 1.1 below the soil surface, and the corresponding drain outflow. So, this H t is known, right, H t is known, and the corresponding Q will be estimated Q k d h by L square, that is 0.001, and H t is the formula, we know the formula. So, use this formula to find out the next time intervals, you know, H, but knowing the H t minus 1 we know H 0, right, and then other values. So, we estimated these values like e power minus alpha delta t, and this value also estimated, and this value also estimated. Okay. And our delta t values will get it from the table. So, we will go to the previous the slide. So, this is the slide we need to concentrate. So, here the day 1 our days are on the first column, and the rainfall on the second column, evaporation on the third column, and the rest we need to estimate what is the recharge, water table head, and drain outflow. Okay, these things will be estimated. So, the given values 0 at 0th day, and the next day you have 0.005 rainfall, and the evaporation is 0.001, and the recharge will be 0.004. That is the difference. The difference of this minus this, you get this one, and then just I mentioned 0.1 we estimated the water table head based on the W and H. Okay, so, that is the water table head we estimated, and the corresponding I mean the inverse formula we estimated the 0.001 as the Q. Okay. So, this is H 0 and this is Q 0. So, knowing this H 0 Q 0, so I mean the recharge R, right. So, here if you observe Q, so for example, H t, so this one H t, so this is known, right, R delta is known, and we have estimated this, okay, and we have estimated this value, So, all values are known, just substitute in and you get this one. Okay. Similarly, here we have estimated this value, this value, and Q naught, and you can find out this Q t. So, like that for each row you can estimate the recharge HT and QT values. Okay. So, this table will give the for a particular day what is the water table head and what is the drain outflow. Okay. So, this is the advantage of this exercise. So, this is all calculations you can go through. H1 is estimated by knowing the H naught, right. This is H naught, and then other values like E alpha naught, and this is the recharge, and this is the value you get from here, and this is the value from here. So, finally, 0.16, and using H1 you can find out H2, okay, and H3, H6 all are similarly the Q1, Q2, Q3, Q4 values. Okay. Right, all right. So, at the end of 10th day, so Q is equal to 0.002, which is the evaporation may be expected to expected to start evaporation. So, then after that evaporation is going to start here in the 10th day, because this is equivalent to evaporation rate. Okay. So, this is all about the lecture. So, in this basically we focused on the water table situation in case of an unsteady state condition. So, first we found the Glover-Dumm equation in case of falling head water table, falling water table condition. So, this is happened when the irrigation is taking place, right. So, that is the thing. Then other one is Hellinger formula for sudden like fluctuating water table. So, for both the cases we derived the equations for spacing. In case of Hellinger formula, so we will be finding out both water table fluctuations as well as the drainage water fluctuations, and we have shown that fluctuations through by solving a problem. Okay. Yeah, thank you so much.